Two solutions that give the same output can take 1,000 times more time to run, and in the interviews the fast one gets selected. So even if you're able to solve the problem somehow, if it is taking more time to give you the output, our effort is unrecognized. So we have to learn to write the program which is structured, optimal, and which takes lesser time to give you the output at all times. Welcome to my interview ready DSA. Here I'll try to solve important DSA problems in detail, which helps you crack DSA focused interviews, helps you learn how to think in interviews. We will cover all required patterns to solve DSA related problems and any other that comes in between. Let's start with time complexity. We'll take an example problem which is given a number, find the count of factors of n. Okay, find the number of factors of n. So first of all, what is a factor? A factor is a number which divides another number exactly, which is with no reminder. What does that mean? If n modulo I is equals to 0, the I becomes the factor of n. Okay. For example, let's take 10 and 10 modulo 5. What's the reminder that we get when we divide 10 with 5? Which is 0. 5 2s are 10 and we get the reminder 0. So which means 5 is a factor of 10. So now let's take these two examples. What are all the factors of 10? It's 1, 2, 5 and 10. And what will be our output for the given problem to find out the count of factors of the given number? It is 4. Fine. And for 34, it's 1, 2, 7 2s are 34, right? So like 2, 17 and 34. And the count becomes again 4. So here, if we carefully observe, the factors of a number are always ranging from 1 to that number itself, right? So what can be the brute force approach here? That we have to traverse or visit each number for 1 to n. Okay. The solution is simple. If we write the code for it, the simple brute force approach. Doing we keep our counterpoint as 0. We start our counterpoint with 0, and for I is equals to 0, I less than or equals to n, I plus plus, what we have to do is, if we just see n modulo I is equals to 0, so modulo gives the remainder of this division. It's equals to 0. We will just increase our counter pointer, and if not, we'll do nothing. And then once we exit from the loop, we will print count. This is simple. So does this solution work fine? We give n value as something like 10 power 18. Like the input size can range from is equals to, let's say, 1 to 10 power 8. We are saying 10 power 18, which is nothing but 1 less than or equals to n less than or equals to 10 power 18. So this is the range of the input size. Will our program execute better for each of the input size? How do we find that? Basically depends on the language, the OS that where we are running our program, the memory of the system where we are running the program, CPU, cores, the number of cores it has, RAM, etc. etc. But is it a good idea to uh, consider all of these external factors in order to decide upon an algorithm that we are writing? It's not right. It's not. So basically what we focus on in the algorithms are the loops the loops that are running based on the input size. And in general the standard is that um, 10 power 8 iterations takes 1 second to run. 1 second to run. It's basically 10 power 7 to 10 power 8. It's basically 10 power 7 to 10 power 8. This is the general standard that is followed irrespective of the external factors. Okay, so in this case, for input size, third case, for input size, if n is 10 power 8, our iterations are also 10 power 8, right? Because we are running our loop for n times. If the given number is n, we run our loop n times. So iterations becomes 10 power 8. And what's the time? It's 1 second as per the general, as a standard. What if the same input size is 10 power 9? Iterations are also 10 power 9. What's the time? If for 10 power 8 it's taking 1 second, for 10 power 9 it's 10 power 9 into 1 divided by 10 power 8, right? Which is equals to 10 seconds. What if it's 10 power 18? Iterations are also 10 power 18, and 10 power 18 divided by 10 power 8, which is equals to 10 power 10. What is this representing? If we convert this 10 power 10 seconds into our human readable times, it's around 317 years. You see how different that is making? 317 years. Will we wait this much time to execute our program? So in order to reduce the time to get our output, what is there in our hands? Input size we can't change, but number of iterations can we. So it is the only thing that we can focus on to reduce in order to reduce overall time. So how can we optimize this? Do we really need to check for each number from 1 to n? Observe carefully. If I multiplied with j is equals to n, both I and j becomes the factors of n, right? Both in this case j is equals to n divided by I, right? And in the example that we solved, number 10, the factors are 1, 2, 5 and 10. The factors always appears to us in terms of pairs, which is here 1 multiplied with 10 is equals to 10 and 2 multiplied by 5 is equals to 10. And here if we see the relation carefully, when we are processing number 2 itself, if number 2 is a factor of 10, there has to be an another factor which is pair of that. So when we are processing 10 modulo 2 is equals to 0, when we check this, it is true. And at the same time, we have to find out the pair factor of it. How do we find out? It's nothing but 10 divisible 2, which is number 5. So now 5 is a factor and number 2 is a factor. Let's take another example, number 24. For 24, the factors are 1, 2, 3, sorry, 1, 2, 3, 4, 6, 8, 12, and 24. These are the factors of this number. Here if we see 1 multiplied with 24 is 24. This becomes a pair. 3 and 8 becomes a pair. 4 and 6 becomes a pair. We already seen this, right? If I multiplied j is equals to n, j is equals to n divided by I. So while processing the numbers till here itself, we will find out the value of j with this formula, right? So here let's say I and j, if we take for I1, 2, 3, 4 in 3 and 12, 2 and 1. If you see here, by here itself we found all of our factors. So there is no need to iterate over all these numbers. There is no need of this. Now let's see how many iterations this approach takes on. If we observe, this I is less than j, less than j, less than j, less than j. So for this, like we can say is like I is less than j. We know that j's formula is like n divided by I. And if we multiply both sides, I into I less than n, I square less than n. And if we take root on both sides, I is less than root n, which means we can check, we can process the numbers till less than root n. Still there is a catch here. For example, if we take number 100, let's process I and j. 100, 2, 50, 4, 25, 5, 20. There is another one, 10, 10, 10. Here exactly this 10, what is this I? Is I less than root n? I less than what I'm saying 100. I less than 10. No, right? This I is equals to 10, which is like we have to process still less than or equals to 10. And in the case of root of that number, there are no two factors, there is no pair, but both numbers become same. Count is equals to 0. We wanted to process till I equals 1, I less than or equals to root n, I plus plus. For each of this iteration, we have to check if n modulo I equals 0. And when it is divisible also, we have to check for this no root value, which is nothing but if I is equals to n by I. This is j. If I and j both become same, if I and j both become same, which means there is only one factor, the pairs are same. Count plus equals to 1, and else it has to be, we have to count twice, right? And this is over, this is over, and then we can print count. For this overall, how many iterations we are taking? Root n. So let's calculate the let's calculate for the input 10 power 18, which was taking 317 years. Let's say iterations input size, if it is 10 power 18, our iterations are root of 10 power 18, which is nothing but 10 power 9, which is nothing but, which we already calculated, right? 10 seconds. So this one we reduced from 317 years to 10 seconds. This is the power of optimization. That's why interviewers care about optimal problems so much. So in the same case, like how do we compare two algorithms? We have already seen that based on iterations we will get to know about the time that it takes for the input. So we consider the iterations. The I Let's take few examples and find out how many iterations it takes, the code takes. If we take this part of code, so it is running from 0 to n and printing it. So this one takes n iterations. Okay, that's easy. And coming to this code part, we are iterating from 1 to n. That's true. 1 to n. And for each number, we are again iterating from 0 to n minus 1, right? Sorry. So for each number, we are again iterating from 0 to n minus 1 and then printing the, and then processing something. Okay. So for 0 is iterating from 0 to n minus 1, and then from 2, for 2 it's iterating from 0 to n minus 1, 3 it is iterating from 0 to n minus 1, and so on till this one 0 to n minus 1, which is nothing but here how many iterations, n iterations, n iterations, n iterations, n iterations. So these n iterations are of n times. These are n, and these numbers are like n times n. N into n, which is n square. And see how about this code part. We run an iteration n times, and we are running again n times, which is nothing but n plus n, which is 2n. Nice. How about this part? For each of the iteration we are dividing the n by 2. We are dividing it by half. So what happens if n is something, in the next iteration it becomes n by 2, and in the next iteration it becomes n by 2 by 2, n by 2 by 2, which is nothing but n by 4, and in the next iteration it becomes n by 6, and so on. So what is happening here? n by 2, n by 4, n by 6, n by 8, and so on till till 1. Let's assume this is happening for k times, which is k steps it is happening. So if we represent this numbers in terms of 2 parts, 2 power 1 it will become, and then n by 2 square, n by 2 cube, n by 2 power 4, and so on, n by 2 power k. This is also like 2 power 0 we can represent. So here this n by 2 power k will become 1, right? Until then we will run this loop. So which is nothing but n by 2 power k is equals to 1, and n is equals to 2 power k. From a logarithmic formula this becomes k, so which is nothing but log n base 2 is equals to k. So how many times, how many steps we are running this loop is log n times. Log n times. Let's take another example. So here we see what is happening. For each, for the first loop it is from 1 to n. And for each of this, the inner loop is from 1 to I. So for 1 it's like 1 to 1, and here it is from 1 and 2, and here it is 1 and 2 and 3, and here it is 1, 2, 3 and 4, 1, 2 to 5, and here it is from 1 to n, right? Here it is 1 iterations only. Okay, here it is 2 iterations, 3 iterations, 4 iterations, 5 iterations, 6 iterations, and so on, 10 iterations, and we have to sum this one which is we have to find out 1 plus 2 plus 3 plus 4 plus 5 and so on till n. What is this number? How do we find this? There is a simple trick. Let's assume this is equals to sum, and the same we can also write as something like this, right? N minus 1 plus n minus 2 plus and so on 1. If we sum these two, if we sum these two, it becomes 2s. What is n plus 1? It is n plus 1 plus n minus 1 plus 2 becomes n plus 1, and n minus 2 plus 3. This also becomes n plus 1 plus, and it continues as the same, and at the end also it's n plus 1, right? Here, how many times we are summing this n plus 1? This is n times. So what we do is like it is n into n plus 1. Okay, but we want only s, which is a single sum, n into n plus 1 by 2. So this many iterations our program is running, right? Now let's understand time complexity and big O notation. Let's say we have an algorithm 1, which takes 100 log n iterations, okay, and algorithm 2, which takes n by 10 iterations. Now if we compare the graph here, this is n log n, which is 100 log n, and this one is our n by 10 graph. So if we see here till 9110, the n value being 9110, till here n by 10 is giving the best time comparing to 100 log n, but after this threshold n by 10 is like growing exponentially, right? But n log n is still gives us the best time. So among these two, which one we have to consider as a best? So we always take worst case value of n. So if we take a worst value of the n, we see that 100 log n gives us the best time. And what big O notation says is that we always have to take the upper bound time complexity of an algorithm in terms of input size. So which we consider as worst case scenario, worst case value of n. For that, whatever is the best time, we will consider that algorithm. So in order to find out big O notation of any algorithm, we first will find out number of iteration that we have seen in the previous examples, and we will neglect the lower order terms from the number of iterations. So let's say if we have n plus or n square plus n, we will ignore the slower order term, and this will become n square only as a big O notation. And let's say if we have n cube plus n square plus n, big O notation for this one equals to n cube, I will ignore this one and this one as a lower order terms. And what's the third step is that we will ignore the constant coefficients. Let's say n plus 3 is the number of iterations. We will ignore this constant coefficients and it will become n only. And another example will be from our above graph itself, 100 log n, right? 100 log n. Here we will just ignore this constant coefficient and this will become log n. On the same graph, if we take the example of n by 10, which is nothing but n multiplication with n 1 by 10. If we ignore this constant coefficient, this will become n. So this way we calculate the big O notation of an algorithm. Now let's see the basic comparison order that we have already. Let's say in here, if we see here, log n is the best solution, gives us the lesser time comparing to root n, and root n gives the best lowest value comparing to n, and it goes on n log n root n square, n cube, 2 power n, and then n factorial and n power n. We just have to have this as an idea so that when we are solving the problems based on the big O notation that we got, we can compare two algorithms. And the graph looks something like this. And let's talk a little about space complexity as well here. So space complexity is nothing but the extra space that we use as a function of input size. It can also be analyzed using the big O notation that we discussed before, that we will calculate what's the extra space that an algorithm is taking, and then we will represent that as an big O notation following those three steps. Let's take few examples here. What is the extra space that we are using here? One is the sum variable and one is this I variable, but these two are like constant, they are not growing in terms of n, so it's just order of 1. If we take this example, we are using a new array, an extra space of array of size n. So based on the size of input, this array size will also be increasing, and then we are processing something, so it's order of n, extra space. And here we are declaring a matrix itself, so it grows, and based on the input size the space will become order of n square. And at last, I wanted to discuss about TLE. This is a common problem that we face when we are solving DSA problems. We submit a solution and we get TLE. So what is TLE? Time limit exceeded. So there is some time limit that our algorithm has to run, but it is failing to run within the time bound. So what is the time bound? It's generally 1 second. Our algorithm has to complete its execution in 1 second for any input number that is given in the range. So for example, if we take the input size from 1 to 10 power 5, for this input, let's see will our algorithm works fine for the time complexity is given. So if the time complexity of the algorithm is n cube for this given bound, if we calculate 10 power 5 power 3, it becomes 10 power 15. Will 10 power 15 run in 1 second? We already know that 1 second is for number of iterations from 10 power 7 to 10 power 8, right? So it's beyond that. 10 power 15 is beyond that, and it can't run in 1 second. So this algorithm will not work. And if we take a algorithm of time complexity n square log n, 10 power 10, it will become n square 10 power 5 power 2, and then log 10 power 5. Here itself, this is not less than or equals to 1 second, so this will also not work. N square, which becomes 10 power 10, this will also not work. And if we take n log n, which is 10 power 5 multiplied by log 10 power 5, this one comes around 10 power 7 to 10 power 8. So we can say that it's okay, this one can work. Yes, this works. This way we have to always check whether our algorithm or approach is will work fine for the given input constraints. So whenever we are trying to solve a problem, we have to first check the constraints of that problem, and then based on that we have to decide like whether we have to check for the better approach to reduce the time complexity. So that's all about this video I wanted to discuss. Hope this is helpful. I'm open for any suggestions or feedback for making this playlist. We'll see you in the next video. Thank you.